All right, with delays in starting the computer, we're ready to talk about, well, actually, let's look. We're going to have a makeup lecture on Friday with all this stuff. And then today we're going to talk about passive noise shaping and in particular offset matching and linearity, and that's section 6.1. How was today's homework? Easy? Bong Shimon? It, it was easy? All right. Okay, I just want to make sure I'm not challenging you. Jan, was it easy? Well, is it the one with the 4-bit? Well, with the 4-bit, I'm going to have to do this in an angle. With the 4-bit, you start out with smaller VLSB, right? So you expect the noise to be smaller to begin with because you've got 16 levels versus 2 levels, right? Now notice it's not going to be perfect. I mean, you're going to have to simulate for a long time. Not a long time, shouldn't be bad, but I mean, it should give you the basic idea, right? And then you can use the output of the DAC to have the signal and the quantization noise to do the FFT on that, right? Instead of adding another DAC. So the signal you fed back, the output of the DAC, you can use to show that. Does everybody follow that? Okay. What's that? Yeah, 4 bits. It should follow the theory, but you have to keep in mind that, well, two things. If you plot on a dB scale, you're not going to see much of a hump. It's going to be flat because 20 dB is 10 to 1, right? So if it's going up, it'll be hard to see. So you need to plot it on a linear scale. And then your peak noise, it's not going to be like the 1-bit where you get a lot more noise when you do the derivation. Well, wait, is it it's passive, right? And you're looking directly at the output of the DAC, you're not looking at the output of the RC filter, because if you look at the output of the RC filter, that's going to influence the spectrum because yeah, so the output of the DAC. Yeah, so if you look at that, you should see noise shaping. You should see less noise at lower frequency and more noise at higher frequencies. Now, because of the distortion term, I'm not sure what the spectrum is going to look like because it's not just going to be signal, noise, period. It's going to be signal, noise, and distortion. What's that? Yeah, so that's the thing. I don't know what the passive is going to do. What do you mean? If you put in a DC signal? Yeah? Yeah? Well, it could have tones or something in it and be tony if it's a DC, and that's a problem with the right. So with Nyquist, you just get single tone out, right? Really? Well, it depends on the level. What's that? Wait, the DAC should go from 0 to 0.875. What? Of 1.125. And then volts. So you should be able to go 0 to 0.875 on the input. Yeah, that makes sense. If you put above 0.875, it's going to give you a tone out because it's always going to be saturated and railed. Yeah. Does that make sense? 612. Wait, but are you putting a D? Why don't we do it? um, let's do the problem. So, what's that? Yeah, yeah, you want to get rid of that term, but let's do the sim and look at it. I mean, I don't want to proceed if things aren't making sense. This one's 6 maybe. Well, it's going to vary a lot with the single bit too. Really? Well, let's see. Okay, so I'm going to modify this one. Okay, so wait, let's go to 0.4 so we don't have that saturating problem because you'll get tones in the output. All right, so that's run. What's that? No, no, I know. I'm just going to compare apples with apples here. I'm not following what you're saying. All right, let's modify this. Is everybody cool? So I'm going to get the scissors out, or why don't I save this first as and we'll get the scissors out here, and I want to get rid of this and this, and then I'm going to move this out of the way. And then I'm going to go grab a 4-bit A to D, ideal 4-bit ADC. So I'm going to grab that, actually I'm going to make it so that it's, yeah, it's good enough. We'll grab that. And then I can pull this over here. Tell me when you don't agree. And let's do a little copying. So you understand, nobody, these passive things, there's not people designing with those, all right? So there's room for creativity and doing things because they generally want to use active, which you'll see why, okay? All right, so I'm going to go grab this, and then I'm going to grab the DAC. And why don't I do that, and then we'll do a little stretching, and then a little copying. And again, a little stretching. Oops. Okay, so does anybody bothered by me putting well, we got to get rid of this obviously because that's our DAC in the other case, and then we got to make sure we have negative feedback. Is anybody bothered by anything here? Is anybody bothered by me looking at this signal rather than the digital representation? It's the same thing, right? This is just the digital. Okay, so let's see. If this goes too high, this code goes up, this goes up. So ooh, that doesn't work, does it? Okay, so let's look at it again. If this signal goes up, this code goes up, this voltage goes up and we get positive feedback. So the way I've got this working, it's not going to work. Anybody understand or not understand? Okay, so if this goes high, would everybody agree this code goes high? Would everybody agree this voltage then goes high? Everybody agrees I can't feed this voltage here, which is analog, to a digital inverter. That's wrong. Okay, I'm seeing confused looks. Is that, what's that? We got to invert. We got to invert the word here. What? Well, let's find out, man. What? If you invert, here, let's do it cheating to begin with. This won't work. This is positive feedback. This is wrong. Okay, so what I'm going to do, just wait, before I move on, I say that and I assume everybody knows. Does everybody understand why this doesn't work and it's positive feedback? Yeah, this is wrong. Yeah, so let's fix it. Let's do it 2 steps. I'll do it once. It's really simple. I want to invert the analog signal, right? So what I'm going to do is I'm going to go grab a control voltage source, and I'll fix it in a moment. And let's do a control R, or control E, and control R, control E, and I'm going to do this, okay? Oops, why is that? Guess you can't plug that in like that. Press G. Boom. Oops. Boom. And value is let's just do -1 to invert. And then, of course, if I had 600 millivolts, what is the inverse of that? 400, because it's going to inverse around the common mode. Does anybody not understand that? So 800 would inverse to 200. So I can't use this circuit without putting the common mode voltage there. Oops, shoot. So if I have an output of 500 millivolts, VCM is 500 millivolts, what does this become? Oops, I got to add one more thing. 0, which is wrong, right? So I got to add one more thing here, which is so if this is 500, this is 500, the difference is 0, 0, 0, then VCM goes out. If this is 600, then I get 600 minus 500, which is 100, plus 500, or times -1, which is -100, plus 500, and I get 400 here. Yay or nay? Does that make sense? Okay, Wenlan. If I have 300 here, this is 500. So what is the difference? What is this? Oops, I got this thing flipped around. Shoot. Sorry. We'll do this. How's that? Is that better? All right. So let's see what happens. Wait, before I move on, is everybody cool? Okay, so we'll go run. And then let's plot V out, or V int. Plot V in and V out. Wait, something's not right. So let's see, V in is the green, V int is that, and then this is V out signal and noise. Oh, shoot. Can't put the V int here because then it subtracts VCM instead of adding it. I got to fix it. Does everybody see the issue? So let me put this back at, does anybody see the issue? So before I was adding the common mode because I thought the plus and minus were flipped around. So now I got to flip it around. So let's do Control R, Control E. Let's do that. Then we want to move this, and then move this. I could have left it the way it is, but this makes more sense. So I get this minus VCM times -1 plus VCM here. How about that? What I had the problem before is I put the VCM on the plus terminal. Instead of adding to this voltage, it was subtracting. Okay, it's this. I want to invert this, right? So if this is 600, I subtract 500, which is 100, times -1, which is -100, plus 500, which gives me 400. Yeah, I could play around here a little, but I've got to take the difference between this voltage. Does that make sense? So one more time. If I have 750 here, what I want here is 250. Okay, so if I have 750 minus 500 is 250, times -1 is -250, plus 500 gives me plus 250. Let's try it again. What? It should work. Let's see, V out S and N. So let's do this. Let's push this here, and then let's look at the output. That's right. Yeah, but this is right. So I must have done some other problem. Let me just make sure there's not any, there's no issue with like converting to 2's complement or anything like that here, right? No, the output should track the input. So when I go here, what? Really? That's not right. No, it's gotta work. I mean, hold on, let me think. Um, all right, so let's try what you said. What? No, I know I want to save as so I can go back. I don't like drafting, so I like saving as. So let's get rid of this. What's that? Say again? It's fine if I don't. What? Alright, so let me think. Maybe I was wrong. And so this goes too high. This code goes up. If this code goes up, this is going to go up. If this is going to go up, it's going to push current in here. Here, let's do this. Let's go a slower frequency. What? Something's not right here. Let me look at the code, because I must be not understanding this very well. So let's do B0, B1, B2, B3. Add plot plane. So we'll go Which one was first? Are you sure? Now this one's got to be plus 5 plus 3.75 plus 2.5. Oops. Okay, it's high. The output goes high. And we need to stop. I don't understand that. And the other thing is it's not really doing noise shaping because the integrator is just basically following. Wait, something's not right because it's just basically doesn't even have this connected. Is this resistor? Okay, there's that. Well, you guys, if you have the same thing, but you understand there's no noise shaping this resistor. It's not even like this resistor's in there. Here, I'll show you. If I go 10 gig, so basically the resistor's not in there, and I rerun the sim, it's exactly the same. That's not right. You shouldn't be doing that. Does everybody see that? It's no difference. Yeah, but this has got to be something stupid. Let me think for a sec here. Okay, I'm not following what's going on here. So sine wave 0.4, 500K, Vint, Vout, bits, Vout sample and hold, 10K. So let's do this. Let's change this to a DC. And if I'm right and I put 600 millivolts in and it's positive feedback, it should go to the rail very quickly. How is that possible? Wait. If well, wait a sec. Yeah, if this (6.4B), yeah. -1 plus j omega RC. Well, but the problem is if I look at this, there's no noise shaping here. It's just basically converting. And so maybe it's because there's a dead zone. Does everybody follow what we're looking? So I look here, the input's at 600, the output is at 563, whatever, okay? If you do the difference, 600, 563, there's going to be some intermediate voltage there. It's going to sit there, right? And the output code is never going to change. So let me think about this for a moment. Is there any way I can... Okay, so here's what we're going to do. Since we're burning the whole lecture time, let's fix this, and I'll introduce a new topic, and then we'll come back next time and we'll go through this, since today was kind of frustrating because of the computer issue. So what I'm going to do is I'm going to replace this integrator here, the passive, with an active. And when I do that, it's going to give me a negative forward path, so I'll get negative feedback here. So the output will be inverted from the input. So we'll get rid of this. So this is what I said, people don't use the passive, and the only time I've seen it is with 1 bit, and maybe this is why. Okay, so we'll go grab, let's do File, Open, and then let's go open this thing, open this, and then I'm going to copy, let's just copy this right here. Okay, so the big difference here is that error that I have in the passive modulator is going to accumulate in this guy. And so I used 10 pico before as well. And so now the output of the integrator is going to keep rising until the DAC changes, the output of the DAC changes. In other words, Vint goes to 0. So if there's a difference between this voltage and this voltage, there's not going to be a dead area. It's going to just keep accumulating until it forces this loop. Now this has negative feedback because if you do, the forward path has a minus sign in it. So if you push a current in here, the output goes low. That drives these bits low, which drives this low, which then pulls the current out here. So you get negative feedback. The issue is when we plot this signal and this signal, it's going to be inverted. So our transfer function from V out to V in is going to have a gain of -1. Does everybody follow that? So I'm going to go ahead. Are there any questions on what I did there? So instead of using the capacitor to sum or sigma the currents, here I'm using the integrator because now this node doesn't change. Then the currents come in here and will cause this to go in the opposite direction. So I hit run, and I'm going to plot the input. Boom. I'm going to plot this terminal, which is moving around. Then I'm going to plot this terminal, which is moving around as well. It should, but it should average. And I could put an RC on here, and it should be average to 600, minus the inversion. So if it's 600, it should be 400. Okay, so let's put, does everybody follow that? So let's go back here and put a sine wave back there at 500 milli, amplitude 400 milli, frequency 100K, hit OK, hit run, and now that's what it should look like. Does everybody follow? And I've got negative feedback because of the op amp. Looking good? All right, are there any questions on this? What's that? How come we have to limit this? Because the output of the this one? This one. This is, oh, Vint. Yeah, it's going to ideally stay at 500 millivolts because the active component here will feed back, and so it wiggles this around. And then you can look at the output. Well, we did look at the output, right? This V node. It's this thing. Yeah. No, I've never seen that. That's why I put it in. I was saying the only one I've ever seen is 1 bit. But I don't want to give you problems where I know the answers, right? I want you to think, and I want you to, oh, well, and then if I try this, I do this. The big benefit of the passive is you don't have the op amp. So you basically could have static power if you were using switch capacitor, zero static power dissipation. So you could come up with something that works really, clever, that, is something worth publishing. So it's seriously, if you have a switch capacitor and you can do a data converter and there's zero static power dissipation, which you can only have in a passive topology, you can do A to D conversion nice and slow and power it off of the light in the room or something like that. So so yeah, when I do the problems, I don't go, I know the answer, I'm going to have them do this, and that's what I want. I want them to think, oh, what's the problem and all that. So all right, let's try to get through in the last 20 minutes the section 6.13, and then what I'm going to do, let me look at the let's get rid of that. Yes, get rid of this. Yes. What I'm going to do is let me look at the homework. So this one's due on Monday, 6/7, October 22nd. So let me look at what we're going to cover. So today, I'm going to readjust the homework since we're not making as much progress as I want, and I'll probably move the one that's due on Monday to next Wednesday, and then I'll split up the one on Wednesday and make it a little, just 1 or 2 problems, and I'll also try to get the projects assigned. But let's talk, and I'll readjust the lecturing as well. But let's talk about offset matching and linearity, and then we'll come back and talk about this next time. But I do want you to start working. I think you know enough that you can start looking at your projects. Okay, so 6.1, offset, linearity, and all that stuff. So with a passive modulator, so let's first look at offset, or no, let's first look at resistor matching. So resistor mismatch. Some of this is going to be pretty straightforward. So you have 2 resistors coming in here, what I use in the book, RI and RF. Then you go to a comparator, and we got our plus, and then I'm going to use the offset here, which the comparator just offset simply means that instead of this switching at VCM, it switches at VCM plus or minus the offset. And then we have our V out, and then that comes around here. Oh, I got the DAC in here, don't I? VREF minus and VREF plus. And before I go on, just tell me intuitively, what would you expect if these 2 resistors are not the same? Yeah, you get a gain error, right? Why? Because if they're not the same, if your output's averaging to your input and you have different resistances here, then if this resistor is smaller, your output has to be bigger. If this resistor is smaller than this one, your output has to be bigger than, smaller than your input, right? And if this resistor is bigger, then your output has to be bigger than your input in order for the feedback signals to be equal. Does that make sense? Okay, so if I go through and I do the derivation, what ends up happening is for the signal transfer, and I'm not going to write this because we don't have the time, the signal transfer function is RF over RI times Vn all over 1 plus j omega RC. And so that indicates that the output signal is, this is the V out. If this signal's bigger, V out has to be bigger. Okay, pretty straightforward. Are there any questions with that? Okay, what about the offset? What do you think is going to happen with offset? Well, think about it for a sec. Well, it changes the switching voltage, but what am I going to see in my output? Well, it's going to linearly change with the offset, and I want to show you that. All it's going to do is add or subtract to your signal, okay? So I want to look at figure 616, and I want to just put some of these things in there, all right? Just because I think the simulations, you can look at the equations, but looking at the simulations may be more useful. So let's go here, download that, right-click there, extract here. And then I go 616, and this one has a filter, so it's going to run. It's going to take a little bit. Why that's running? Did I do a? I'm going to stop this. All right, you can see the figure in the book. I want to see what the other one looks like. Switch capacitor version 2. Okay, this one I'm going to use because it just replaces the digital filter with an analog. So I hit run, and you can see the average of that. There's a dead zone right here I'm going to talk about briefly here in a moment, but I want to just come in here real quick and change the resistor. So if I change this to 20, so RF is 20, what do you expect is going to happen to the curve based upon what I said here? It's going to get steeper, right? Because the gain's higher, and the gain is the slope of the curve. It's the slope, the RF over RI. So I hit run, and you're going to see once it starts taking off, it saturates, and see how the gain went up. Any questions on that? And then if I go the other direction, 5K, you say, oh, gee, you're not challenging me. That's going to mean the slope gets smaller. And so there you see, and actually you can see a bigger dead zone. Again, I'm going to talk about this briefly in a moment. Whoops, I didn't want to do that. And then if I change that back to 10, and I'm going to put a big offset in just so you can see it. Go grab the voltage source here. Control R it. Oops, why is that? Oh. Get the scissors. Right click there. I'm going to put 100 millivolt offset. And I claim it's going to shift the curve. And hit run. Whoops. Save. Save. Close. Run. And does everybody see the blue went up by, on average, 100 millivolts or so? It's non-linear, but you have that issue here. If I go the other direction, put a minus 100. So it just linearly shifts things. All right. Yep. So you hit run, and you'll see it go the other way. Okay, so does all that make sense? So I want to talk briefly about the dead zones, and I probably will talk about this one more time. But you notice in, let's put this, get rid of this thing, go back to the original state. Hit run. You notice that when I'm around the common mode voltage here, that I'm getting where the output is repeating. If I look at this output right here, let's just zoom in. If I look, it's just going 1 0 1 0 back and forth, and the output kind of stays fixed, right? So it's going 1 0 1 0 1 0. This isn't as big of a problem, and maybe I'll show you the analog modulator here in a moment for the analog topology. But what happens is, because this node is wiggling around and it has a certain shape, that when you put in a voltage near the common mode voltage and this voltage changes, that because this voltage is changing, the average amount of charge that you push in here can be equal to the output amount fed back when it goes 1 0 1 0 1 0. Okay, so what I want to do is I want to go back and I want to put in the, or actually we can just show this with a here, let's see, we'll use an analog integrator, and let's use We'll look at figure 631, which is the equivalent of this, what we're looking at right now. Okay, so wait, let me back up. Does everybody understand that what happens is this voltage wiggles? And so if I move V in towards 500 and this voltage is too low, it'll move up, and the amount of charge that I get it through here will vary because of that variation. So if I have 10, 10, 10 here, and it's feeding back, I can get the situation where the amount of charge, because this is varying, that flows in here is equal to the amount of charge that flows back through here, and it sets up these limit cycles or sets up these oscillations where it just bounces back and forth and it's happy. It's not that this isn't moving and my input's putting in a charge that's fixed because this isn't moving and then this isn't moving, or this is moving back and forth and I get the same amount of charge. So did that make sense to anybody? So if I was at 600 here and then this starts going up towards 600, the amount of charge that I get through here is starting to move towards what? 0. So if I have 600 and this starts moving towards 600, the amount of charge I get through here starts moving towards 0. If I'm at here going back and forth 10, 10, 10, well, then I can get the situation where this is moving around, where because even though my cycle's repeating over and over, that charge that flows through here can be equal and opposite to the charge that's flowing in here. So if this was at 600, this started charging to 600, and then this node was at 0, well, I'd start pulling a charge out, and those charges could be equal because of this variation. Does that make sense? In simpler terms, if you like math, it's this. You're getting the case where Vin minus Vint over Ri is equal to the average of Vout minus Vint over Rf. Because this is varying of time, it's very possible for this to be true, and so when it is true, you get the repeating cycle. Okay, so does that make sense? No? All right, we're going to cover it again. Does that totally seem crazy, Yan? All right. Okay, so let me go show you the equivalent of when we don't let that node move, which is 631. It won't be as big of a problem. Yeah. You can still have dead zones. Yeah, yep. There can still be that situation because your time varying things, and the output of the integrator is varying. So let me show you this, which is the same plot we just had, except now I'm using a op amp here. Notice in order to get negative feedback, I put the inverter in the background, but notice how I flipped the minus and the plus so that Vin and Vout will be the same polarity. So if Vin goes up, Vout will go up because the forward gain is positive. So all that's happening now is this node is not going to be wiggling, so I won't get as big of a dead zone. So we'll hit run, and so we go up, and as everybody see, we'll go right around this part where we had problems, which was 0.5 volt. And you can see I get a little bit, but it wasn't like the passive modulator. Does everybody see that? And you can see just looking at this that it's much more linear than what I had with the passive modulator. Any questions? So if I were to ask you why, I'm getting rid of the distortion term. I'm now holding Vint. Let's plot Vint. I'm now holding Vint constant. It's not wiggling around. I don't have this situation here where things are changing. Any questions? You say, oh, but there still is a dead zone. Sure, but look how small it is. Now, when we talk about second order modulators, which we'll talk about next time, it further randomizes the tones and you really don't have a dead zone. So I want to show you one just real quick based on a second order modulator. I guess I don't have, well, maybe I do. Not really, because the difference in that analogy is when I dump the cup of water into the bucket, the level of water in the bucket doesn't influence how much water is in my cup, right? In the passive noise shaping modulators, because the capacitor voltage is varying, Vint is varying, it's like I'm not pulling a whole cup in, I'm only going to put part of the cup in depending on what the water level is in the cup. You follow me? Okay, so yeah, I fill it up or dump all the way out so that the level in the cup doesn't change. Well, now, because the water level in the bucket is influencing how much water I take out or I put in, I'm getting error, and that's what the Vint is doing. All right, any other questions? Let me look real briefly at a second order modulator just to show you. And let's look at so many figures. I don't want to sim that one. Lots of drafting. This one is here I'll just show you and then we'll put a ramp in there. And let's put a ramp to be consistent. Let's put a ramp that's 50 microsecond rise time. So we'll go pulse 0 to 1, delay 0, rise time 50 microseconds. So that's a ramp. Then we'll go sim for 50 microseconds. We'll start saving data at 0. Okay. And I think that's all we need. So we hit run. And let's see what our filtering does. Oh, let's get rid of this dude. And let's put a little more filtering there. Let's go 1 nano. Should reduce that noise by a factor of 10. Can't make it too big because then you get a delay. And you can see it's not as flat, meaning there's not as big of a tone there with the second order modulator. And again, we'll cover this later. Okay, any questions? All right, so what was the next topic we were supposed to cover? You know what? I'm going to go ahead. Does anybody have any questions on any of the homework or the test or anything? So what I'm going to do is I'm going to move this one here to here. Then I'll probably move this to here. And then this to here. All right. I don't want to, I got to keep on schedule, and then we have issue that's important for us to discuss and we don't discuss it, because I think that was useful to talk about that 4-bit passive and the issues there. Okay, any questions? Yes? No, I think it's because of this issue right here. I think what happens is that when you have the 4-bit DAC and 4-bit ADC, you can get the situation where Vin minus Vint is equal to the Vout minus the Vint, and it always works. So you get the situation where, oh, okay, I get, say 600 millivolts here, then it comes in, and this is at, let's say, 550 millivolts, and then my feedback DAC's at 500 millivolts, and I get 10K, right? So you look, it's the exact same thing. So here I get 50 millivolts over 10K. Here I get 50 millivolts over 10K, but then I look at the voltages. This is 600 and this is 500, and they're supposed to be equal. Okay, so when I have the 1-bit DAC, it's not as big of an issue because this moves around. You follow me? Does anybody follow that? So this is why we have that's why that 4-bit DAC wasn't working. That's the same thing as we have here with the tones, except I put DC in here just to show. Any questions? I'm not seeing every light bulb's clicking on with this. Is anybody following this? No? All right, so let's spend a few minutes on it, more on it. So, would you all agree that when I had my Here, let's just do this, all right? Let's go ahead and pull the sim up and look at it because I saved it, which was in here. And that was, which one was it? Version 2? Nope. When did I save that? Oh, no, sorry, I saved it over here. And 6.6, right, this one. So let me take this and just put none, DC value 600 milli. Oh shoot, that's not what I want. That's the one with the active. That's not the one I want. Which one? Oh, okay. So let's go ahead and put this in here. None. 600 milli. Okay. And I hit run because I'm inverting. I need that inversion. I hit run. I plot. Okay, there's VN 600. There's my output, which is bouncing back and forth. So averaging to 470, whatever it is, right? So if I look at the current through here, let's plot minus, I get a value. Does everybody see that? Add plot plane, and then I plot the current through here. And I get a value. Should have just left them both negative. And I get a value. So if I look and I say, okay, well, how are these two currents related? I press Control and left click. This is 6.82 microamps. Control and left click. This is 6.82 microamps. The averages are the same. Wait a sec, this is constant at 600 millivolts, and this is basically bouncing from 400 to 550 or whatever it was. So yeah, after I do the inversion. So the averages are right, but because of exactly what I showed right here, got 600 here, 500 here, so I get 50 over 10K, I get 50 over 10K. The two currents are equal. Does that make sense now? Wenlan, does that make sense? I'm not, okay, this is one where I'm not following what the issue is and it not making sense. So let's see. Does everybody understand? Let's plot here. Let's go pull this up. And then let's plot this voltage, and this voltage. So if I look, let's delete this plane, delete this pane. If I look, this voltage minus this voltage divided by 10K is what? I'm asking a trivial question. This 600 millivolts minus this voltage is what? Okay, this voltage minus this voltage is what? Divided by 10K. It'll make it even easier. It's the current through here, right? The current through here is this voltage minus this voltage divided by 10K. And they're equal. So when they're equal, nothing changes, even though it's wrong. Yeah, it's dead. It's going to sit there, and this current flowing through here is going to equal this current, even though this is at 600 and this is at average 400 or whatever. It's the same thing I see here. This is 600, this is 550, this is 500. I think in our case, this is 600, this is like 500, and this is like 400 or something like that. So this current plus this current equals 0. I mean, they're equal and opposite, so there's no reason for the loop to change. So it's going to sit there, and the code on the output of the DAC, or of this DAC, is going to stay the same. It's not going to do noise shaping. Does that make sense? KB? All right, let's quit. So look for a change in the homework and everything else. And I'll try to get the tests graded tonight before I leave.